very high power, because the current was always flowing. You were just switching the current. So it made it really fast, but it also made it very high power. We had pushed the cooling technology and the packaging technology pretty much to the limits at the time. And we needed packages where you would put 100 of these small chips on one MCM, and you'd have 4 of those, and that would make up a processor. Meanwhile, in the CMOS world, you were able to put a whole microprocessor core on one chip, or we're getting to that point. So there was a real economic challenge there. And so in November of 1992, almost exactly 20 years ago now, IBM made this very bold decision to shut down the bipolar technology development, to shift all of the processor design into CMOS, and really to radically restructure how we developed these mainframes. For those of us that lived through it, it was a rather traumatic time, sometimes referred to as a near-death experience for the company. That's not an exaggeration. I got lots of war stories from that era, which I would be happy to tell on the breaks and the rest of the week here, but not right now. My point here, and the reason for bringing this up, is I think this episode holds some interesting parallels and lessons for us today. Through all of that time, the conventional wisdom was that the mainframe was dead. All right? Client server was taking over. That model was going to be able to do everything. There were new languages, new paradigms, all the old stuff that was on the mainframe, it'd sit around for a while, but it would just kind of die out. And the consultants and the analysts were debating when the last mainframe would be unplugged. Not if, when. All right. Turned out, however, that there was still a need for that kind of processor. There was still a need for that enterprise centralized computing model. All right. There were a lot of established, very business-critical systems, software architectures built on that model. The processor speed still mattered, and it was still faster. You could still build faster processors with ECL than you could with CMOS. And the centralized control was still the most efficient scaling model for many workloads, and it was the most. No, I do not have slides. Sorry. It was still the most efficient scaling model, and it was the most efficient operational model for many businesses. Right? So, because of that, there was an opportunity for IBM to transform the mainframe, and we were successful in rebasing it on CMOS. The model weathered the storm, the limitations of client-server kind of became apparent, and the centralized and distributed models learned to have a peaceful coexistence in the IT industry. A lot of coming back to the centralized ones, particularly for what are now called systems of record, the ones that really run those back-end databases and transactions. So here we are 20 years later. It's 2012. IBM is still designing and shipping mainframe systems. We're showing off our designs at Hot Chips and ISSCC and Micro and all that good stuff. All right. So we got through it. We're going on, kind of back to where we were. What's not so obvious, I think, unless you were really in the middle of it and following things closely, is that we didn't get there just by changing technology and continuing what we'd been doing before. We had to make some very significant changes in the direction and in the designs in order to succeed in that transition. Right? We needed processors that were designed specifically and optimized around high-performance, full custom CMOS. All right? We spent a lot of time looking at whether we could just take the old designs and remap them forward. And again, I can tell you a lot of stories about the debates that went through that. It was a very long process to come to the conclusion that we really did need something that was designed for full custom high-frequency CMOS. Things that did not depend on the characteristics of ECL logic, things that did not depend on complex clocking schemes, that did not depend on the horizontal microcode, large control store, tight one-cycle loops. There were some things that just weren't going to scale well into high-frequency CMOS. All right? We needed a new core design. right? And we needed to do it from scratch and targeted for that. We also needed a new microarchitecture approach with that, something that was simpler, something that relied on a new kinds of internal code to do the complex kind of operations. We went to something called millicode that really just looks like the assembler instructions, so it could use the same pipeline and we could keep the overall design much simpler and more compact. We needed a straightforward, comprehensive checking and recovery design. And we also needed to embrace open standards. All those things coming along, we couldn't just ignore them and we're going to say in our mainframe niche. We needed to bring in IEEE standard binary floating point to complement the hexadecimal floating point. We needed first-class support for C and C++ and Java and the other languages coming along. We needed to open up the standards on network and I/O. We brought in Linux on the mainframe. And we made a bunch of system architecture changes, in particular supporting what we call parallel sysplex clustering to complement, not to replace, but to complement multiprocessor scale-out. So we had to make a lot of fundamental changes to how we did things. And I'm convinced that without those changes, and I said there were some long and heated debates, to put it mildly, within IBM about many of those. But without those changes, I think it's doubtful that we would have succeeded in that transformation. And it's pretty certain that I wouldn't be here talking to you today. All right. So now, that's the history lesson. Now, 20 years later, here we are in 2012, and we're at kind of a new crisis, or inflection point, if you will, in these designs. Maybe it hasn't quite reached the point of crisis that it did for IBM in 1992 with the bipolar-based mainframes, but it's getting there. So from a CMOS silicon technology point of view, I think it's fairly well documented that we are at a crisis point. Moore's law continues. We can keep making the transistors smaller, but Dennard scaling, to refer to it, has ended. In fact, it really started ending, depending on who you ask, about 10 years ago, when we've been gradually deviating from that. Now, just quick lesson for those of you that don't know what I mean by that. Moore's law says that we keep shrinking the transistors, every litho node. It used to be about every 18 months. Now it's about every 24 months. We can put roughly twice as many transistors in the same area. Dennard scaling is the recipe that another IBMer, Bob Dennard, came up with for scaling all the various dimensions in there, including the voltage, in order to be able to track that shrink. And as you shrink by a linear factor of alpha, you get alpha squared more transistors. You take the voltage down by alpha, you shrink all the dimensions by alpha, the frequency goes up by alpha, and when you're all said and done, the power density was constant and life was good. All right? Those were the fun times of CMOS scaling, because you just take in the new node, you put in a few more tweaks in there, you leverage those extra transistors to throw a whole bunch more features in there, and you got wonderful scaling and didn't have to worry about things. Problem is that, physically things don't all scale that way, especially atoms don't scale real well, and we're down to, small numbers of atoms for some of these layers. So we had to stop shrinking some things, and that means we had to stop shrinking the voltage if you want the performance to go up, but that means the power density has been going up like crazy. And we're pretty much at the limits of what we can do there now. We've kind of hit the ceiling on power density for supplying the current and for getting the heat out, and now we have to just go with that, what we can get out of size. And the net of that is that we can keep making things smaller, but we probably can't keep making the transistors faster at that constant power density. Right? That's an important inflection point. It changes how we look at things going forward very drastically. All right. At the same time, and this might be a little more controversial, I don't know, but I would assert that on the microarchitecture front, a lot of the classic techniques are largely tapped out. Let's take branch prediction, one of the favorites there. Back in the 80s, I remember when that was a brand new thing. And in our earlier designs, it was a little piece of logic off on the corner of the core. As the pipelines got deeper, as we we're trying to squeeze more performance out of there. That branch prediction has grown to be one of the largest chunks of logic in the core, even as the cores themselves have gotten significantly sized. There's been a tremendous amount of research. Many of you have done that. I don't know, Yale, how many papers have been published on that over the years? Probably hundreds. How many of you read? Thousands. So a lot of good stuff. But we're kind of we're well past diminishing returns, I would say. We're kind of out of gas in terms of really new breakthroughs there. Similarly, I'd say on the superscalar front, we've seen our designs go from one-lane roads to 8 or more lane superhighways. Wonderful advances there, wonderful innovation in being able to manage all the dependencies and all the things crossing back and forth there. But again, we're way past diminishing returns in performance per square millimeter, performance per watt. And outside of really, really well-behaved code, I think we're past what compilers can really squeeze value out of in terms of ILP. Similarly, on the out-of-order front, we've seen those windows grow from 16 or 32 instructions up to 128 or more. Again, lots of good innovation in managing all of that, but the physical and the logical complexity involved are getting very daunting, and again, well past diminishing returns. Interesting to note that all three of those were around back in that bipolar era. All three of those were in the last bipolar design that we did. Maybe not well recognized, but we had them in there, kind of ahead of, they were kind of ahead of their tools in a lot of ways, so it took us a while to get it right. And all of these have been studied and researched and permuted and pretty much wrung dry, I think. Now, as we've done that, oh, you say no? You disagree? Good, good. I want to be controversial. If I can't get Yale to disagree with me, I haven't succeeded. But as the thread speed diminishes, the thread speed growth has been diminishing. There's been a lot more turn on multi-core and multi-thread, and you can see that being one of the top areas of papers submitted here. And those design approaches are great, and they're very valuable, and I think there's going to be a lot more advances there. But it's important to note that they don't help the thread speed. In fact, generally they hurt thread speed. They tend to push an awful lot of the scaling burden over onto the software. And in and of themselves, they offer relatively little value for going from one generation to the next for enterprise scale kind of computing. Maybe they offer a lot of value if you're talking about a single socket thing and the amount of stuff you can do in one socket. But in what you can do in a larger system, the incremental value of that from one generation to the next is much smaller than what we've been used to in the past, just from driving the capacity. Right. And all of that kind of points to one other aspect of this crisis or inflection point, if you will, and that's an economic one. Each new silicon litho node is getting much more expensive to design, to develop, to debug, to get right. And each one is delivering less and less in terms of incremental performance and even density. We're spending more and enjoying it less each new generation of CMOS. And each new design in the business world is taking a huge investment. So even with all the improvements that we've had in design tools and methodology and all of that, it's still taking an army to develop one of these things. And it's taking more designers, more verification engineers, more test cycles, more test systems. It's getting very expensive. All right? And if you look at it, I'd say we're really not on a sustainable model just to continue on business as usual. At some point, it's just not going to be worth it to be doing new processors, which is not a good prospect for those of you looking to spend your careers in this field. All right? So I think we need some changes. And there are a lot of parallels then, I hope you can maybe see them already, between now and 20 years ago. We've got increasingly expensive technology. All right, we've run into some technological limits, especially in the area of power density. And it's not just a cooling problem, it's also a current density, current supply problem. All right, we've got some new models of computing that are challenging the enterprise central computing model. 20 years ago, it was the distributed client-server kind of approach. Now it's more the seas of racks of 1 or 2 or 4 socket kind of servers, maybe even micro servers based on very, very small, lightweight cores, deployed in some kind of cloud configuration. All right. And once again, as 20 years ago, a lot of people are saying, do we still need faster CPUs? Do we still need systems specifically designed for enterprise scale and enterprise computing? Does the processor architecture and the microarchitecture still matter? So again, I think we're at an inflection point. The distributed model can do lots of things. That cloud model is extremely powerful as a way to deliver capacity. All right? And a lot of things around that highly distributed, I'll say super scale out kind of approach can do a lot of things that used to be the domain of mainframes and enterprise computers, no doubt about that. All right? And there's a lot of things you can do with a whole sea of very lightweight threads. All right? But I'm going to assert here, and this is, again, I expect some disagreement in the audience, but I'm going to assert that there's still a need for enterprise scale servers, and that there's an opportunity to fill that need with new kinds of innovations in microarchitecture. All right? Enterprise clients still want fast threads. They actually want them faster and faster, but at the very least, they want them not to slow down from one generation to a generation, because the transactions that we're doing are getting richer. They want to do more and more work inside those transactions, more real-time analysis, more real-time fraud detection on credit card transactions, for example. We're getting more and more complex algorithms around these business processes. All right, the batch windows of wanting to get a bunch of stuff done in a certain amount of time are still there, and the amount of work is growing, and sometimes the amount of time available is shrinking. All right, and you can do a lot with software parallelism, but just as Moore's law continues, Amdahl's law also has not been repealed, and there's only a certain amount you can do with that, at least without Herculean effort on the software side. I would also assert that enterprise clients, big customers, the banks and financial institutions and large companies running very large complex operations, they still need enterprise qualities of service in their systems of record. They need reliability for 24/7, round the clock, round the year, never go down operation. They need scalability for these growing transaction workloads. They need manageability. They need to be able to operate things simply and not have 1,000 different servers to shepherd all the time. They need security in both the hardware and the software, and the network and the storage and memory. And they need robust compatibility. And I'm going to come back to what I mean by robust compatibility later on. They need that. And they need the stability and the continuity. And they need very controlled incremental changes from one generation to the next. So I would assert that there's a huge opportunity in the microarchitecture field for meeting those challenges, but I think it's going to mean that our processors, especially in the enterprise area, are going to look different now and going forward, in the next decade, if you will, than they have for the last 20 years. Right? So the challenge I want to focus on here, and spend the rest of my time this morning on, is how do we adapt the art of processor design to this new world for enterprise processors? What do we need to do? What are the things that we need to change, we need to focus on? All right. All right. Now, some of these areas I'm going to talk about, there is a lot of activity. I look at the list of papers, the categories in there. I look at what's going to be presented this week, and it's touching on a lot of these things. Some of them I'm not aware of there being so much work going on. But all of them, what I've seen, and maybe I'll change my mind with what I see this week, but what I've seen in general is that there's a lot of good work going on in these areas, but it needs to be translated into the enterprise IT arena. It needs to be grown and hardened and matured to where we can really get those qualities of service that we need for enterprise IT clients and apply that. So I want to start with what I see as the biggest challenge in this, and the one which I'll say right off, I have the least clear picture on what the answer is. Right? But I think we need to focus on processors that are going to scale well into the single-digit nanometer kind of world and scale smoothly. All right, the Moore's law continues, but Dennard scaling is ended. The transistors are going to keep getting smaller, but they're not going to be getting faster. All right, and what's going to make things tougher is that logic and arrays and wires and whatever other elements you want to put are not going to scale the same way. Right? They're going to have different shrink factors. They're going to have different speed factors, whether they're speed up factors, or in some cases they might even be relative speed down factors as we go forward. All right. Now, we've had uneven scaling. Any of you that have been in the industry and have taken a design and moved it forward, you always get some uneven scaling, and some things get faster by bigger amounts than others. Now, that's nothing new. What's new is that the base on that is smaller. It used to be you're going to get this much speed up, and now it's going to wiggle around in here, and that's not too big a deal. You can adjust that. When the amount that you're getting is near zero, and you're getting uneven scaling across that, that means some things are actually getting slower or harder. Right? And now you're much more sensitive. Your signal-to-noise ratio, if you will, has gotten to be really, really small. You're much more sensitive to those variations. All right? And I think that's going to prove especially true for some of the large, complex structures that we've come to depend on for our performance. Think of these multi-level, wonderfully complex branch prediction schemes that are out there in all the leading processors right now. You think of the big, large window, many issue instruction sequencing units out there. Again, they work really well. We've gotten really good performance out of them. But I question whether they're going to scale with the kind of linearity and consistency that we're going to need to be able to take them from one generation to the next. And yet economic factors are going to dictate that we be able to take designs and move them from one to the next without having to rip them up and redesign them every time. Otherwise, we're going to get to that unaffordability point on development much, much faster. All right. So at the same time as we got this problem with this variation and how things are going to scale forward, well, enterprise customers need performance consistency. This is one of those robust compatibility elements. When they move from one generation to the next, they need things to perform roughly the same or better. And the relative performance of different things in their software stack need to be fairly uniform, and that's got to be true across a wide range of workloads. Otherwise, things get out of balance, and they end up having to go do a lot of tuning or reworking of things, and that becomes a disincentive for them to bother to go to new hardware. All right. If I look back again 20 years ago, when we went from bipolar to CMOS, we had to abandon some of the structures that had served us really well. We had to go to, simpler designs, simpler pipelines. We had to completely change the way we did complex instructions and the kind of internal code that we use for those. And we had to do all of that in order to have something that would scale well for high-frequency CMOS. Right? I think at the point where we are now, we need to go and re-examine the things that have gotten us where we are and had that same kind of, is this really the right way to scale going forward? All right, look at some of those structures. Look at some of those methods and methodologies that have served us really, really well. All right, and figure out how to adapt those or change those, replace those with ones that are going to scale well as we can scale the density of CMOS without, again, getting the kind of speed up that we had back in the good old days. Right, without getting voltage and frequency scaling out of it as well. I don't know exactly what this means for our processor designs. So I'm tossing out here a challenge for which I don't, question for which I don't have the answer. Right? I do believe it is one where there's a huge opportunity, right? And one where if we can, get the right innovative breakthroughs, it will be of great value. But I think our processors in the future are going to look somewhat different from what we have now. All right. Another area that comes from that, another challenge that comes from that change in the technology is a challenge around reliability. And I was happy to see on the program that there is at least a session on fault tolerance in here. That's good that we're getting that focus. You know, in the enterprise IT world, reliability isn't a nice add-on. It's not something that, it's good to have on top of everything else. It's an absolute necessity. It's got to be a comprehensive kind of reliability. You know, some people say, well, we'll have, we'll figure out what pieces of software really need to be reliable, and we'll run those twice, and everything else will be tolerant of an occasional failure. Which part of your bank's software stack do you not care about being reliable? Think about that. In the enterprise world, it's much harder to carve out pieces and say, well, I only care about it on this part. They care about it for all of it, or at least they're not sure that they don't care about it for any of that. All right, so we need to have a scheme that is comprehensive, that doesn't depend on sacrificing performance in order to get reliability in a few places. It needs to be across the board. All right? It needs to be end-to-end reliability, system-level reliability and availability. Again, we've come to expect these systems to be up all the time, to be always available, and the cost to businesses when things go down is very high. And above all, there has to be absolute data integrity. First, lose no data, make no wrong answers. Better to crash than to give a wrong answer, but then you're not allowed to crash either. So it's always been a challenge to get to these levels. It's always been one of the things where we spend a lot of time in enterprise designs going after it. But I think the new world is going to make it harder. All right? To start with, these smaller devices are going to be more vulnerable. We're already seeing that. It used to be you only had to worry about faults like from radiation and such in arrays, and maybe register files. Right? Now, it's in latches. And we can, we've done work where we take our things and we go, assault them with high energy radiation to try to accelerate that and see where the failures can happen. And we see, latches, can trip now because the charge that's holding the information in there, that Q crit has gotten much smaller. It used to take like an absolute direct hit from an alpha particle or something to flip a latch. Now even a glancing blow might do it. And particularly in arrays, things are getting small enough where the probability of flipping multiple bits with one event, which used to be kind of astronomical, you could just ignore that possibility. That's not astronomical anymore. It's definitely within the realm you have to worry about. All right? At the same time, with the processes that we're using, as these, we shrink these things down to, 14 and 10 and 7 and who knows where we're going in nanometers. The complex processes going in there are getting harder and harder to control. Right? So it's another case where the variation has gotten bigger even as the base improvement has gotten smaller. We used to be able to build in a fair amount of process margin and a fair amount of operational margin in our systems. You're going to make sure you're not too close to the edge. Then you're going to test these things, take it all the way up to the edge, and then you're going to back off from that, and that's what you ship. Well, if we try to keep those process margins and operational margins in our systems going forward like we've had in the past, we're not going to have anything left to deliver that will actually be going backwards because those variations are getting bigger. All right? So we can't afford to have those margins there anymore, and yet we still need to be reliable. So we need designs that are much more tolerant of higher failure rates, soft rates and hard rates. And it's going to be harder to know just where to focus our fault checking. It's got to be everywhere. Right? One of the things that we've done in the past that served us well when in the transition into CMOS for a few generations was a very coarse-grained kind of checking. I'll say, let's just take this whole unit and replicate it. All right? Get 100% checking on those units. That's great. But then we had to abandon that because it got to be harder and harder to keep things close enough together to do that. We started taking those mirrored copies and kind of putting them on the outskirts of town. A cycle away is not too bad. When it was going to be multiple cycles away, that was going to get way too hard to keep track of everything. And that kind of brute force, coarse-grained approach burns power, and power is becoming much more a critical resource. So we had to drop back to more fine-grained local checking. We're going to have to keep doing that. We've got to find ways to do it efficiently, extremely efficiently, and still be doing it comprehensively. Again, there's nothing that we can count on being reliable anymore. Right? And along with that, another challenge I would toss out there that I don't think is getting addressed real well, at least I've not seen on it, is we need tools to measure how well we're doing that in the design. Now, that might not seem like a hard thing until you've gone and tried to do it. To actually analyze a design and say, how well checked is this? Doing that analytically turns out to be very hard. And I think there's a huge opportunity if we could do it. We depend on simulation right now to do a lot of that testing of how well our checking's doing, and that's going to get more expensive and harder to do. So I think an efficient scheme for measuring how well we're checking things, as well as efficient schemes for doing the checking, will be important. I do think that the way that we've been doing recovery is good enough going forward. You kind of preserve the state, treat the processor as a state machine, preserve the state. If there's a failure, you just refresh it from that hardened state. If the whole core fails, you take that out and drop it into another core. I think that was one of the things that we changed going into CMOS that has worked very well. I think the good news is that that's fairly scalable going forward. The hard part's going to be knowing exactly when we need to invoke that recovery. Right? Another kind of scalability that we need to focus on, and again, this is one where I see a lot of work happening, is with much higher levels of multiprocessing and being able to do that linearly. So with individual processors, at best, growing very slowly in speed, maybe not growing at all, those big enterprise scale kind of workloads are going to need more and more processors to get their work done. So we're able to put more processors into the same area. We can solve that problem. The challenge is to make sure that the real work that gets accomplished grows linearly with the number of processors. Now, there's a lot of attention being paid to that. Again, my observation is that a lot of that's focused on relatively scale-out friendly kind of workloads. Some of them even focused on what I would call embarrassingly parallelizable workloads. Getting that linear scaling for a large number of processors in data-intensive kind of workloads, the kinds of things that are running databases, transactions, all of that all the time, I think that's a lot more difficult, and there's a lot more room for growth there. Now, those kind of codes tend to be dominated by data dependencies. They're dominated by data structures that are shared across all the processors and all the processes. Right? The software running those is built on a fairly strictly coherent kind of model. Now, on some platforms, it's relying on the hardware. On others, it's relying on some explicit things in the software to enforce that coherence. But it's still, either way, you've got a bunch of serialization and synchronization points that have to be managed. And as you go from, ones to tens to hundreds of processors, managing that and doing that linearly gets to be a lot more difficult. All right? So I think we need new mechanisms, new ways for software to be able to scale past those serialization points, whether it's serialization around memory data structures, or whether it's serialization around things like translation look-aside buffers, where you need to make sure that everybody's using the same translations from virtual to real memory. Right? Now, one of the things that has been done, where there's been a lot of work, is transactional memory, or as we called it in our systems, transactional execution. And that's, this problem was exactly the motivation for including that in the latest mainframe. There's a paper on that in the session this afternoon, I believe. All right. And that's an important step forward, but it's just a first big step there. There's a lot more I think we need to do off of that starting point, and a lot more opportunity to allow software to scale well to many hundreds of active cores, of active threads, without requiring huge changes in the software architecture. All right. One way for, one reason why we can't do the change in the software, I almost missed a point here, is that we need something, again, called robust compatibility. What do I mean by robust compatibility? I mean not just architectural compatibility, but performance compatibility. Smooth scaling from one generation to the next. All right, so this compatibility idea has been a big part of the mainframe architecture. It was one of the breakthrough things with System 360. As I say, we've been application program compatible since 1964. We have made some changes in the architecture that required OS changes, going from 360 to 370, and then to XA, and then to Z architecture. But even when we did that, and we do that about every 20 years, even when we do that, we've been supporting both architectures for several generations. I mean, there's a very slow rate of change on architecture in this world. And it's not just because we're old stodgy mainframes and we don't change much. It's because the customers do not want to change much. Their software changes are extremely expensive for them to deploy. All right? They've got very complex architectures. They've got all these different pieces fit together. It's very difficult to test changes thoroughly, and especially to test them at scale. They can test them off in their sandbox logical partitions, but still not be sure what's going to happen when they switch over to that and Monday morning everybody comes in and the market's open and all of a sudden you went from a few thousand transactions per second to a few million transactions per second, and you're trying to figure out how to handle all that. All right. And because these things are used for business critical applications, business critical operations, they really don't want to be, well, let's just try it and see what happens. Outages are extremely expensive and to be avoided if at all possible. All right. And even something that seems to us as simple as recompiling code to take advantage of new architecture or new hardware features or whatever, even that can be expensive and hard to justify. And this is an interesting conversation I have with customers sometimes there, because even if it's just recompiling and we've got a certified compiler, they're still going to have to go through a full regression test. All right? And there's an expense and time and effort that they can't be spending on other things. And if you go to a customer and say, well, I need you to do this so that things don't get worse. I need you to go spend a lot of effort and time and money doing something to make sure things don't degrade over time. That's a tough sell to them. They want to be making things better and doing new functions and moving forward. So they don't want to change anything that they don't see as broken. Right? And they're looking to their suppliers, whether it's IBM or anyone else, or their suppliers of these enterprise systems, to give them systems that will let them grow, get new functions, do more stuff without having to change much. So that's what I mean by robust compatibility. All right? I say there's a performance dimension to that, where across all of their workloads, across all of their operational conditions, things need to scale, need to run faster, need to have more capacity and be able to do more. So here's where one technique that's used a lot in some realms of, and like all of your laptops probably have this now, where when the load is light, you can run the processor harder. All right, if you don't need all the CPUs turned on, all the cores turned on, you can run some faster, you can get more speed out of those and get better performance. But if you get a lot of work in there and you have to turn everything on to get the throughput, well, then you have to slow them down because you're at a power limit. That, okay. Find a place to set it here. At least I don't have a laptop here to worry about. The podium is sloped. Where was I? Across all the technique where you can have the cores run faster in kind of a turbo mode, but then slow things down if everything's active, that's not going to fly real well in an enterprise kind of environment where you say, oh, at the point where you need the performance most, I'm going to slow down your threads. Right? From a software scaling point of view, that's asking for trouble, and at the very least, it's going to give an inconsistency in the way things run. Right? So some techniques that work well in other spaces that don't work as well here. We need to find ones that will allow us to scale the performance smoothly, linearly across all of those operating conditions. All right. And deliver that value. So this is a constraint that we're under. It's a big constraint. It can kill a lot of nifty ideas right from the top. You're like, no, you can't do that because it would break this kind of compatibility. All right. And some of my research colleagues, know how frustrating I can be in that regard. When they propose something, I said, well, yeah, but it'll never get past this test. Right? So the challenge we have is to find ways to leverage new architectures, to leverage new techniques, and to preserve that commitment, that investment that customers have in these systems, to provide that kind of robust, not only functional compatibility, but performance compatibility, protect their investments, provide real growth in the value that these things deliver to the customers in the industry, and to do this without disrupting their operations, without imposing big changes in the software, changes in their operations, big costs and development on their end, and still be able to leverage some of the innovative approaches that many of you are working on, all right, to deal with these technical and physical limitations. One path for doing that I would toss out there to think about, and again, this is an area where there's a lot of work going on, is dynamic optimization of software. A lot of things happening on that and different techniques. Again, most of them don't seem to quite get to where we could use them in the enterprise level. And I want to challenge you to find ways to do those that will meet these other criteria for enterprise computing. But there's a lot of success out there for just-in-time compilation, for dynamic and progressive recompilation in Java and similar environments. We need to find ways to extend that, again, non-disruptively to other languages, other environments, up to middleware, even up to operating systems. And I think there's an opportunity here to put in hardware facilities, things designed into the market architecture that will enable that intelligent optimization and that intelligent dynamic optimization of the software, and even provide some hardware assist for the software to deal with those deep corner cases that make it hard to translate something that works for almost everything except these really weird exotic cases, because you find out that those weird exotic cases, for everyone that you can name, there's some clever programmer out there that has found a way to do something really neat that exploits it. So getting things that will translate from, I'll say, the academic arena into the enterprise arena, get that kind of robustness in there is what we're looking for. And I think this is not just a software problem. It's sometimes addressed that way. But it's an opportunity, again, to put things into our designs that will cover those corners, that will be robust and thorough, and will enable us to take advantage of some of these things in commercial processors. So to the extent that we can create these mechanisms that will give us rigorous, thorough, provable compatibility and have minimal overhead, I think that will then free up the rest of the microarchitecture design from some of these other constraints. If we can hide it around some dynamic optimization and around covering of these corner cases, we'll be able to turn loose the microarchitecture to do other more novel things in there. And that'll let us get more effective value, more effective performance out of these systems, even when the nominal performance growth is slow. All right, so we need to look for ways to optimize the code in real time, on real code for real workloads, with the current hardware under all kinds of operating conditions. And I think if we can do that, then it will open up more opportunities for adaptive hardware. Again, another area where there's been a lot of, I'll say, academic research, a lot of good activity going on there, but we need to translate that into the enterprise world. We look at things like composable multi-core kind of things, reconfigurable accelerators. If we can translate those into that robust compatibility so that we can take advantage of that without having to rework the software, without being disruptive to customers, and get them from where we are now into that world, I think it'll open up a new avenue for growing performance over time. So mostly I've talked here about the stuff that's on the processor chip, I'll say, microarchitecture proper. I think we also need to design into our chips, into our processors, ways to anticipate advances in what I'll call the surrounding technology elements. And we see some of that in some of the work that's being presented this week around memory, new types of memory, new form factors for memory, but new kinds of accelerators and special purpose hardware, being able to integrate those smoothly. Optical interconnect, which always seems to be 2 generations away from being economically practical in our servers. Right? One of these days, it'll be 1 generation, and then it'll actually be there, and we need to be ready for it. Packaging for higher density and lower latency, and integration of different kinds of technologies into what looks to the rest of the system like one processor. So there's a lot of examples of these. They've been around for a while, and I say sometimes it seems like they're always just a few years away because we keep finding ways to squeeze out value from the existing technologies. All right? But we need to be anticipating when those are going to be ready, because it's no longer, well, I'll do the best processor I can, and then I'll see if we can apply some of these other things. Now, the value going forward is going to come in large measure from those things outside the core itself. And we need to be ready to take advantage of them when they become practical, when they become economically scalable and applicable. All right. One way to do that, again, another requirement, another challenge I would put out there, is to develop more modular and adaptable designs. Right? Ones that can take new things in there, can reuse most of it, but bring other things in and do it efficiently. I mean, modularity isn't too hard to design. Modularity that's efficient and high performance is difficult. Right? But it's important, besides bringing in these other technology elements and getting value out of that, it's also important for the last challenge that I'm going to mention here this morning. And that is, we need an economically sustainable development model. I've kind of alluded to this before. This isn't something that necessarily comes up a lot in conferences like this and more academically oriented ones. But the fact is that high-end processor development is becoming an extremely expensive business. Right? Some of that comes from that extremely expensive silicon technology, and I say spending more and enjoying it less with every new technology node. But we can't blame all the expense issue on technology. Some of it comes from us. All right? It's driven by us, the computer designers, the design engineers, because all of those brilliant microarchitectural things that we think up and do papers on and present and put into our designs and get us a little more performance, they drive more designers. They drive more verification engineers. They drive more circuit engineers, more integration, more test systems, more turns of the crank to get it right, more months in development, right? We need to take a larger share of our engineering efficiency juices. Right? That's what engineering is solving problems efficiently. We need to turn more of that, I think, onto the design process and the design methodologies and the design approaches, right? So that we come up with designs that are fundamentally verifiable, composable, scalable, adaptable, reusable from one generation to the next, and be able to take advantage of new things that come along around on the outside and be able to adapt to this uneven scaling of technology. Right? I think there's an opening here to rediscover truly elegant processor designs. We've gotten really good at, we had some elegant ideas early on, and then to get more out of it, we pile more stuff around it, and we've gotten these very rich, complex, wonderful designs that we get a lot of performance out of. It may be time to take a step back and say, what is really fundamental there? Can we take all of that learning and come up with something that is cleaner, simpler, more elegant, more scalable, and sustainable going forward? I don't know the answer to that, right? But that's the challenge that I would put out to you this morning. Right? So that's my message. Right? I think we're at an inflection point here in the industry with high-end processors. Maybe somewhat with other kinds as well, but specifically certainly with high-end enterprise processors. And it's very similar in a lot of ways. There's a lot of differences too, but similar in a lot of ways to what mainframes faced 20 years ago with that transition from bipolar to CMOS. I think there is still a need for these processors and for the systems that are built from them. There's an industry need. There's a desire to stay on the models that work. More and more we're seeing security and reliability and continuous availability be high priorities in this industry. All right? So that's where these, not just IBM mainframes, but other enterprise class processors have thrived, where they brought great value. There's an opportunity to continue that if we can meet these challenges. Right? But to do that, I think our designs need to adapt to the new world of scaling, to where transistors keep getting smaller but not faster. Right? And we need designs that are efficient and evenly scalable, the smaller dimensions, without losing thread speed, that are reliable with comprehensive checking and handling for hardware faults, including ones that are going to be much more pervasive and common than they've been in the past, that enable linear, smooth scaling of real-world workloads to many, many processors and threads, that maintain the functional and performance compatibility from one generation to the next, so that enterprise clients don't have to re-architect their stacks and don't have to change their software, but can get more value out of each new generation. All right? I think they're going to need to support dynamically optimizing the code and being able to get more out of it in real time. We're going to need to be positioned to support new technologies that are going to come along with not enough lead time for us to go do a whole new processor designs. All right? The winners are going to be the ones that can adapt those new technologies and get them to market quickly. And I think we need to do this with a sustainably affordable product development model. Right? I look at this and say, it's a tall order. Right? Some of these points, I'm sure, are debatable. I hope I've done something that will stir some discussion. I know I've managed to omit the favorite ideas of many of you, perhaps most of you. I don't know. Each of you probably think, well, if you just did this, it would solve that problem. Love to have those debates. Some of them I probably thought of, some of them I haven't. Right. And I also acknowledge that my scope here is kind of narrow. It is around one part of the industry, around enterprise processors, mainframes in particular, but really enterprise processors in general. It's where I've spent my career, so it's where my focus is. It is a narrow slice, if you will, from one point of view, but it's a pretty substantial business and a pretty substantial part of the industry out there. And I think there's an opportunity for innovation in new directions there. Right? And I think these are the attributes that we're going to need in those processors going forward in order to succeed. And I think the challenge to you would be that the architects that can come up with the designs that have those attributes, that can leverage this technology, leverage the other developments going on, and do it in a way that provides value from generation to generation in the hardware for these enterprise clients that turn about at the rate of supertankers, that make very slow changes, be able to deliver value into that world through our designs, and that can leverage this with the technology as it goes on down into the single digits of nanometers, and who knows where that ends. I think those are the architects that are going to have real success in this part of the business. And I think there's an opportunity there to apply the collective juices that we've got here to solve some very important problems. So I hope that I have stirred some thoughts here. Hope that this is a thought-provoking and edifying week for all of you, and maybe it'll have a little bit of a contribution to that. And thank you for your attention and your time. I think there's time for a few questions here if we want, and I will be here for the rest of the conference as well. So, thank you.
We have 10 minutes for questions. Hopefully that'll allow ample time. And you have a microphone in the middle. Feel free to come up, state your name and affiliation.
David Wood, University of Wisconsin. Very interesting talk. One thing that we've observed I've observed from a distance in the high-performance computing industry is that there seems to be a convergence starting between, big supercomputers and cell phones, and people are seriously looking at building, massive machines out of things that look a lot like a cell phone chip. Do you see any such opportunity for enterprise computing?
Maybe, but is farther off. And the reason really gets back to the scalability for the shared data transaction kind of workloads. And being able to manage the things that need to be serialized logically. And I stress logically serialized because there are ways around that, like transactional memory and such. But that's going to be really challenging. I mean, we're seeing challenges trying just to get into the hundreds of processors and make that work well. Trying to get into the thousands is going to be, very difficult. So again, I think there's an opportunity that high performance computing tends to be very parallelizable, very scale out friendly kind of work, and there's a lot of good stuff going on there. At some point, we'll be able to shift that into enterprise, maybe, but it's farther out. I say we've got work going on right now where we're trying to take our existing stacks with ZOS and with the usual transaction workloads, and anticipating the problems I've talked about here. We're running those as single image 80 ways right now, which is the biggest the prior generation. Once we get the new generation hardware into that test bed, we'll go to 100 way. But I tell customers when I'm talking about this, don't try this at home. Because it just doesn't, those kind of workloads just don't scale well to that many things going on in parallel. We got to solve that progressively, and we need some breakthroughs even to get to the hundreds. Once we're past that, maybe you'll see the thousands and see that kind of approach, but I think it's farther off.
Thanks.
robust compatibility, which I guess suggests that when Windows crashes every 5 minutes, we tolerate it, and your customers won't. If you hadn't brought up robust compatibility, I would have said everything you had to say is relevant to the whole computing thing. I would have rather your title had been something like, what I learned over the last 20 years in making that transition from bipolar to CMOS informs my vision for what we need to do now across computing for the next 20 years. There's a lot there, I mean, back when I got started, we were counting diodes and
Yes.
how to minimize circuits. Then we went to transistors. Then we went to more complex primitives. Then we went to VLSI, PLAs, et cetera. And as time has gone by, as the technology changes and as the application space changes, you need to be able to think. And too many people are not thinking. So there's plenty of jobs out here for everybody in this room moving. I expect to still be around for at least another 40 years working. And I think there's plenty that can be done. I think you limit yourself when you say, no, I'm just talking about enterprise. You weren't just talking about enterprise. You're talking about everything. And so I should have a question somewhere in here.
Okay, yeah. Can I respond to that? Just I hear and I appreciate the comment and would say I didn't want to presume that my experience translates. I'm kind of hoping that what you're saying is true. I didn't want to be presumptuous on that and wanted to not claim for applicability beyond that space. I think there is some. I think there's some aspects of this that there are other ways to solve that don't apply to for some other spaces that don't as easily apply. But I think you're right that there is applicability that's more broad.
I think it's more than just there's some applicability. I think there's major, when you change the name of the game, if you look at the silicon, we used to think we have rectangles. As we go to nanometers, we have ovals.
Right.
In fact, we don't even have ovals anymore. We have this sort of a thing instead
Blobs.
of rectangle. That's going to change how we design our circuits.
Absolutely.
Moving forward. And it requires a lot more inventiveness and engineering ingenuity, and not trying to do the same old crap, in the new context. I do have one thing I would like you to respond on, actually, since you mentioned the software stack, you mentioned the problems with software, you mentioned reliability is certainly more important moving forward. With alpha particles, you can't trust anything anymore. I've been pushing for a long time, and people who know me well know this, and they tell me I should stop, that people need to understand it doesn't matter where within the hierarchy you work, whether you're working on applications, whether you're working on circuits, you ought to have a deeper appreciation for the whole spectrum in order to be more effective at what you're doing. And I keep getting the pushback saying, no, we can't do that. Your job is to isolate where you are, and assuming that everything below you is, transparent, I guess. You don't know what's going on below you. You work just at your layer. I've been pushing, breaking those artificial barriers, and I wonder if you can comment on that.
I think you should keep pushing that. I agree. And there's a balance there. You can't have everybody worrying about everything, but there does need to be an understanding of what's going on under there. And sometimes the breakthroughs that really let you do something efficiently come from bridging across those. And that's, I'm not a device guy in circuit design. I'm microarchitecture and one more system. But I've really gotten an education, particularly the last few years, working closely with the semiconductor development people, understanding what are the challenges there and why, and translating that back to, okay, what's that mean for our designs? And so I'm absolutely with it. There at least needs to be that understanding of what's going on in those other layers, not just, well, that's their problem, they'll solve that, and assuming they solve that, then I'll do it. There needs to be some factoring of the work, other you don't get anywhere. But there needs to be more looking past those boundaries. I agree. So keep pushing.
Any other questions for Charles? Hi, Daniel McFarland from CMU. You mentioned that the researchers didn't like you because you had go, no-go tests that you applied to some of their ideas. Are you at liberty to tell us what those go, no-go tests are so that we can factor them into our work?
Well, again, and it's not so much go, no-go tests as well, some of it, it's like things that, being able to do across the board, performance improvements, or have consistent performance, or, oh yeah, this will be a great design, but it means that you have to, cast off certain parts of the architecture, and they'll just recompile everything. No, yeah, so those are kind of extreme examples. There's smaller ones in there. Again, it's more nuanced than that in the actual discussions, but there's a lot of, that's a nice idea, but does it really translate? The one I mentioned of being able to dynamically adapt the performance and power and work around that. There's some nice things you can do in some regards, but does it solve what the enterprise customers want? Where they tend to be more concerned is, what's my maximum power? How much power do I have to allocate to this system out of my data center? Because saying that, well, most of the time it uses less, but then it's going to use more. Well, that doesn't help me. If my workload spikes, I either have to shut something else off somewhere in the data center, and then it's hard to manage that, or I'm going to cap what the system can do, or I'm going to blow a circuit breaker. None of those are really good options. So it's a different mindset in terms of the robustness that's needed. It makes for some good back and forth there. There should always be at least a little bit of tension between development and research, or neither one's doing their job.